The last two problems in this test are so awesome, I had to give them their own page each. Number 23 is a sequence problem. Find k given the sequence 2, 3, 10, 15, 26, k, 50, 63, 82. Let me rewrite the sequence so we have more room to write some things. Let me leave k as a blank. So whenever we're working with a sequence, it's a good idea. The first thing is to look at the finite differences between the terms. When I say finite differences, it's a fancy way of saying what is the difference between each of these terms? What's being added to get from term to term? So the technical name for these is finite differences. Also a great way to sound smart. So what's happening? To get from 2 to 3, we're adding 1. To get from 3 to 10, we're adding 7. From 10 to 15, 5. From 15 to 26, that's plus 11. And then we don't know this finite difference. We don't know this one. We do know to get from 50 to 63, you need to add 13. And to get from 63 to 82, we have to add 19. If the finite differences between terms are all the same number, we say if the finite differences are constant, say it's always plus 3, plus 3, plus 3, plus 3 every single time, then it's what we call an arithmetic sequence. This obviously is not an arithmetic sequence, and if you don't see a very distinguishing pattern amongst the finite differences, another interesting thing that we can do is look at the finite differences between the finite differences. Hopefully that doesn't blow your mind too much. That's where it gets interesting. I believe the technical name for these are the second order finite differences. Since we're looking at the finite differences and then we're looking at the finite differences between those finite differences. So let's see what's happening here. To get from 1 to 7, we have to add 6. To get from positive 7 to positive 5, you're actually subtracting 2. To get from 5 to 11, you're adding 6. Now, it seems there may be an interesting pattern forming. Unfortunately, we don't know this, we don't know this, we don't know this. We do know between 13 and 19 plus 6. So it appears that these second order finite differences are forming a pattern, really a pattern that goes back and forth. Plus 6, minus 2, plus 6, minus 2, plus 6, minus 2. Let's see what happens if we were to assume that this is the correct pattern. So plus 6, minus 2, plus 6, this would be a minus 2. This would be a plus 6, a minus 2. Well, what do you know? The plus 6 actually does fit in. So let's go ahead and work backwards from here. Assuming this is a minus 2, this means the next finite difference here in red is going to be plus 9. And then if this is plus 6, the next one will be plus 15. And what do you know? If we do minus 2, we end up with 13, plus 6, we get 19. So it appears that we interpreted that pattern correctly with the second order finite differences. Let's see where this gets us in the actual sequence. So let me go back to blue up here. If we apply this, 26 adding 9, 26 plus 9 gives us 35. And if we did 35 plus 15 as we follow the pattern that we assumed, we do end up with 50. So it appears that everything is fitting in perfectly. And then these second order finite differences, this is really where the pattern is established. It is, of course, the oscillating pattern, plus 6, minus 2, plus 6, minus 2, plus 6, minus 2. So the correct answer is 35. The moral of the story for sequences is look for the finite differences. And if the finite differences are not getting you anywhere, look at the finite differences between the finite differences. Alright, the last problem on the sample test deals with different number bases. These are all expressed in base 7, hence the subscript here, is 7. And we're asked to find the sum of these numbers and express that in base 7 as well. Let me try and briefly explain how different number bases work. Obviously, I have to if I'm going to work this problem out. It's really quite simple. We need to look at our own numbering system at first. So we commonly use what's called the base 10 numbering system, or the decimal system. And all that really means is we use digits, 0 through 9, that's a total of 10 digits, and then in our place value system, we have, of course, the units place, the tens place, the hundreds place, thousands place, and so on. But what those really represent are powers of 10. Units are 10 to the 0 power. The tens place, we're really representing how many units of 10 do we have, 10 to the first power. Here we're saying how many units of 100 do we have, that's 10 squared. How many units of 1,000, 10 to the third, and it will keep going like that, 10 to the fourth, 10 to the fifth. If we put a decimal point there, then we have 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, the tenths, the hundredths, those places. So to kind of compare those side by side, in base 7, which this problem is in, it's a very uncommon base to work in. Normally in computer science we use base 2, which is called a binary system, which only uses digits 0 and 1, or we'll use hexadecimal, which is base 16, octal, base 8. I didn't know the name of this, I actually did look it up, so here's another word for your vocabulary. The base 7 numbering system is what is called septenary. It's the septenary numbering system. Anyway, the whole point is, when you work with place value, we're no longer looking at powers of 10, we're now looking at powers of 7. Oh, and by the way, that implies that the only digits we use are 0 through 6. So this still represents units, again that's 7 to the 0 power. But this now represents quantities of 7. So we think of that as how many 7 to the first power, how many quantities of that do we have. We think of how many units of 49 do we have, that's 7 squared. How many units of 343, that's 7 to the third power. And then, of course, it goes on like that. These are 3-digit numbers, so we only need to look up to the 49th place. There are any kind of number base problem, there's two really good approaches. I'll be honest, one takes a whole lot of math, the other takes not too much, but it takes a lot of thinking. We could convert everything to base 10. Of course, we then would have to add those numbers together and then convert back to base 7. That's the method that requires a lot of steps, a lot of math. The other option we have is add in base 7. So we'll have to kind of think in terms of base 7 momentarily, and we can actually carry digits and do all the kind of regular arithmetic, just utilizing base 7 instead of base 10. This will be a quicker method, much quicker. Alright, now that I've gone over all that, I'm going to erase this to make some more room. I think I'll show the quicker way first, and then depending on whether I feel like it or not, I may show the long way. The quicker way really just, we add using place value the same way we would in base 10. These are all in base 7. So we can add vertically, and we can do some carrying. But we have to just keep a few things in mind. For one, there's no digit that we can use above 6. 6 is kind of like a 9 in this case. So the number 7 in base 7 is actually 1, 0. The reason being, This again is the units place, and this is the sevens place. So we have 1 unit of 7 and 0 units. So another example, number 8 in base 10. I really should be writing base 10 here. That's one of those things that's also invisible. If you don't see a subscript, we assume that we're in base 10. In base 7, the number 8 would be 1, 1. Because it's 1 unit of 7 and then 1 unit. It's really 7 times 1 plus 1. So you could make a list just by counting. You could make a short list of conversions. These are all in base 7. So in the problem we need to add vertically 1 plus 3 plus 6. 6, 7, 8, 9, 10. That's going to represent 10 in base 10, which in base 7 is 1, 3. So just like we would in base 10 arithmetic, we can carry the 1 with the 3-digit right down here. We now have to add 1 plus 6 plus 1 plus 3. That is 11 in base 10, so it's really 14 in base 7. Write the 4 here, carry the 1. And now we just have one last addition step. 6 plus 3 plus 1 plus 1, again, is 11. So that is 1, 4, written in base 7, so this is the answer C, 1443. Now, dare I show the long way, which I mentioned earlier was just to convert everything to base 10 and then converting back to base 7. I'll try to do this in the quickest way possible. It's really a good idea to watch how the conversions work to get more familiar with converting between number bases. So 361 in base 7 we wish to convert to base 10. We have the ones place, the tens place, the 100ths place. Here, in all these numbers, we're going to have the units place, the 7th place, and the 49th place. Converting this to base 10 is then just solving the problem 3 units of 49, or 3 times 49, plus 6 units of 7, or 6 times 7, plus a single unit. That does evaluate to 190. And it is 190 in standard base 10. 1 unit of 100, 9 units of 10, and 0 single units. 613 in base 7. We have 6 units of 49. 1 unit of 7 plus 3. So all of that evaluates to 304. This is 304 in base 10. This is also in base 10. And the last number is 136. 1 unit of 49 plus 3 units of 7 plus 6 units. And that does evaluate to 76 in base 10. So then we add in base 10 190 plus 304 plus 76, 570. The trick with that, and the answer is all in base 7, we have to convert this back to base 7. And that's kind of tricky because it involves division and subtraction. It's a little bit time consuming. Anyway, let's set this up. It's going to be a 4-digit number. So we're now in base 7. So we have the units place, the 7th place. 7 squared is 49th place, and 7 to the 3rd power, 343. So that is a place value as well. 570 does have 1 unit of 343 in it, so what we do is we take 570, subtract 343, and get 227 left over. So if we account for 1 unit of 343, we have 227 left over. We want to see how many 49s are in that. So if we divide 227 by 49, we get 4 point something. So there are 4 units of 49. Now, if we do 4 times 49, we get 196, so we need to subtract 196 here, since we're accounting for 4 units of 49. So 227 minus 196 leaves you with 31. You want to see how many 7s are in 31, so you can divide 31 by 7. You get 4 point something, so there are 4 units of 7 in 31. 4 times 7 is 28, so you need to take 31, subtract 28, see how much is left over. 31 minus 28 is 3, so there are 3 units left over, so we do get 1443 in base 7. Same answer, in my opinion, much more arithmetic. So that is the last of the 2011 sample UIL test. Hope that you've enjoyed the videos. I've enjoyed making them, and let's have a good season.